So this is going to be a lighter talk. It's the last talk of the day. I thought I'll try to make it a little bit lighter. So there's not much of math in the talk. There are 3 equations. A lot of it is based on math, but I'm going to only show 3 equations, and I'm not going to dive into it. I wanted to make this more of an application type of presentation to show you how we're trying to push the computations to extremes. Part of the workshop is about length, time, and accuracy of the materials modeling. What I'm going to be talking about is really trying to push the length and the accuracy of the materials modeling and connect it that way. The talk actually is a bridge between the current workshop and the next workshop, which is actually the bridging between multi-scales. So this is at a level of multi-scale, but again, we're trying to do this computations or pushing the computations to do some type of extreme simulations. I have to acknowledge the people that actually did the work. There are 2 former postdocs of mine, Marcus Sidman, who's actually now at Aachen University in Germany. Eugene Gu is now as a research scientist at A-Star in Singapore. And in addition, I have to acknowledge all the contributions from all the nice work of a number of collaborators at the Naval Research Lab who were doing a lot of the experiments and some DFT calculations that were useful for our study, as well as collaborators from Georgia Tech where they've been providing us with some inputs from atomistic simulations. And the reason as well that I chose this talk is that actually it was at a transition between a past funded center that we had with the Naval Research Lab looking at trying to predict deformation and failure in additive manufacturing, additively manufactured materials, and actually we have an incoming grant as well from NASA, which is another center that involves a lot of collaborations, again, on this topic of additive manufacturing. And the big contribution that we're trying to push forward here with these smaller types of simulations, and how can we actually connect them to these component level type of predictions. So this is really the driver for this talk. But before I go into that, I wanted really to talk a couple of slides here of discussing this idea of interplay between experiments and computational modeling in this realm of material design and engineering. So maybe some of you guys have seen similar plots of these. This is the times length scale type of plot, but we're overlaying on top of it here approximately the domain of applicability of different types of simulation methods, as well as the domain of applicability of different types of experimental techniques. So you can see like the DFT calculations would be down here, atomistic simulations, MD simulations is the yellow region over there. If you do some type of coarse grain methods, regardless of the material system that you're going to be looking at, metals or polymers or whatever, this is typically the type of domain that you're looking at. And then if you're talking about continuum mechanics, it goes up in the length scale for sure, but is not able to capture information at the lower length scales because of the lack of the physics in these continuum mechanics models. And overlaid on top of that, you can see all these types of experimental techniques that exist. And you'll notice that a lot of these simulation methods tend to be at a lower length scale as compared to the actual experimental results that exist out there. You can do some type of spectroscopy that correlates to some degree with atomistics and DFT calculations. However, if you go up to the coarse grain level, maybe then you can start going into transition electron microscopy type of studies or in situ type of studies. You can correlate it with shock experiment or laser shock experiments as well. And you can touch bases with nano indentation and so on and so forth. But you're still, in terms of time domain and typically you would not be getting into the studies related to in situ SEM experiments. Maybe you can touch the bases of length scales down here, but not necessarily the time scales. To take this a step further, the limitations with these types of computations, even when you look at continuum mechanics, you might think, okay, well, continuum mechanics at least tackles a lot of the different types of projects, a lot of different types of experiments that exist out there. Before I actually go to what I wanted to say if you look at the deformation mechanisms in materials, typically that would be the domain of activity of it, which correlates quite nicely with definitely the coarse grain approaches, as well as with atomistics and potentially as well touch bases with the DFT length scales. But if you look at mechanical properties, they span the entire space, right? So it's just to give you a sense of the applicability of all these types of experiments and so on and so forth. Now, I am actually an aerospace engineer. I do a lot of mechanics of materials predominantly. But what drives me, what keeps me up at night and wanted to keep you guys up at night as well is this idea of fatigue, right? I know that everyone flies, so that's why I put this up here to keep you guys up at night in the sense that fatigue is a big issue, and it's not just in aerospace. I look at it from an aerospace approach. So this is the events of fatigue events that happen over the last decade, and the sizes of each particle here represents the type of casualty or the number of casualty. The colors represents if they're fatalities or not. Casualties might mean that someone just got injured. And you can see that these are 4 classical examples of instances that happen, and all of them are basically related to fatigue failure. And it's a very important topic, right? And it's a very, very classical problem. And it actually exists. If you think of any metal or any actual material that you're interested in, typically fatigue is a very important factor for failure of those components or those samples. It all depends on the application, and it all depends on how cheap the material could be. But nevertheless, fatigue is always an issue. So if it's a cheap material, you might not worry too much about fatigue. You might not design it for fatigue. You can throw it away and replace it. But if it involves life, if it involves expensive equipment, expensive machinery, then it becomes a very important problem to think about. And it's still a very active problem that exists. Now, if you look at, again, these types of experiments and simulation framework, but now I actually extended it into into days and minutes and years. Now, if you look at the problem of fatigue and failure of fatigue, this is the length scale that we typically talk about. So it's way off, even continuum mechanics. There are approaches where people are trying to push continuum mechanics and trying to come up with expedited type of predictions to push continuum mechanics predictions into fatigue failure world. But nevertheless, really, most of our understanding of fatigue failure, you can understand fatigue evolution or damage evolution during cyclic loading from these types of simulations. But if you really want to predict the fatigue failure, it's a very complex problem that the models just cannot reach that in terms of length scale or in terms of time scale predominantly. So the big question that I think this community could potentially has the ability to push towards that is this idea that can we push the boundaries of these computations, not just to go a little bit this way or a little bit that way, but really try to reach these types of classical and very important problems, in my opinion. So this was just, again, the motivation of what keeps me up at night. There's a lot of intriguing things that you could do down here in terms of technology, in terms of science, but in terms of where they end, I think really we're really still confined in these lower length scales. But hopefully with further research, the nice talks that I've seen so far and the other stuff, the other work that is going on, hopefully we'll be able to bridge that scale. So what I'm going to be talking about today is really looking at mostly simulations related to this coarse-grained approach and really trying to drive it to be able to do larger length scales that touch bases with the actual component side or predictions of mechanical properties of component side, and how can we actually do that, and how can we extract information out of that that can be useful and important for predicting of these studies. So now switching to the actual topic that I'm going to be talking about today, the actual topic is related to additive manufacturing. The technique is what is known as laser powder bed fusion. And we're looking at a particular material, which is basically 316L stainless steel. So we're basically trying to build 316 stainless steel using additive manufacturing or laser powder bed fusion. And when you do these types of studies of trying to build, so this is just a quick overview of what laser bed fusion is. There are a lot of different techniques of how you do additive manufacturing of metals, so I'm not going to go into it. But the one particular example that I want you guys to be familiar with is this idea of that you deposit a layer of powder and then you come in with a laser and the laser melts the powder locally where you want to create a solid material, and then you can deposit another layer and do the laser melting and repeat that process multiple times until you build a part, which is basically represented here schematically by this darker regions. And if you do that, you can create very complex structures that are typically not possible to achieve if you're doing classical manufacturing approaches. So it's a very unique approach that gives you a very nice type of geometries that are very useful. Now, the intriguing thing with this type of fabrication technique, if you compare the materials that have been generated using this type of fabrication with laser powder bed techniques, what you get is these types of stress strain curves. If you create a dog bone out of this 316L that has been created through this LPBF LPBF technique versus the classical samples of rough samples or as-cast samples, you can see that there's a significant amount of strengthening, but not just strengthening. In addition, you get significant amount of ductility. So this is, again, a representation of these types of experiment, but representing here the uniform elongation versus the yield strength or the yield stress of that material, comparing samples that were generated using this additive manufacturing technique versus those that have been conventionally developed as we've been doing over the last few decades. And clearly you see, you typically wanna, if you're trying to improve a material or trying to push such that the yield strength increases and the elongation increases, and you can see that that pops up suddenly for whatever reason, these materials actually have a lot more elongation and can achieve higher strengths. So experimentally, people have been looking into why these are the cases, and this exact same study has particularly looked at it. And it all relates to this type of microstructure that is developing during this additive manufacturing technique. So what you're seeing here, this is basically your grain structure. This is a few grains types of structure, looking closely with some type of etched surface. I'll talk about it in a minute. And then if you take TEM foils out of parts of these samples, this is the type of dislocation structure that you're gonna see. If you look chemically, these are the type of chemical concentrations that you're seeing in the sample. So what are they actually seeing here that is different than conventional techniques is that if you look closely in the different grains, when they did these etching, they started creating these boundaries that are forming, and these boundaries align quite nicely with these high dislocation density regions. These high dislocation density regions seemingly are correlated directly with areas where, and unfortunately with the projector, there should be like very clear cells right here that mimic these exactly, where you have high chrome and high molybdenum concentrations. So there's some type of segregation of molybdenum and chrome that happen that align quite nicely with these specific dislocation cell structures. So this is the sample after it has actually been fabricated, and this is what they're actually seeing. So there's clearly a multi-scale structure that is forming, and there's a clear heterogeneity in both the dislocation distribution and in case of the chemical concentration within the sample.
Is there an annealing step for those samples?
You can do annealing, but these are without annealing. No, annealing can affect the behavior. It depends on what kind of annealing you do. So, but if you anneal, what a lot of times people have seen is that actually the strength drops. Because what happens is you can have two things. One of them is you actually get a homogeneous concentration of the composition, and you get more homogeneous dislocation distribution. So ultimately, the strength is really driven by these heavy, dense dislocation structures that are forming that seemingly are correlated with these concentrations that are the segregation of some of these solutes in cellular walls.
Sorry, is he saying it was just moly and chrome that were?
Yeah. So in this case, moly and chrome are higher, and I think when you look at iron, what you'll see is that the iron is actually higher in the cell interior, not on the boundaries. So the chrome and the molybdenum decorate the boundaries. The iron is mostly in the center. There is very little oxygen, very little silicon in these samples, so they're not necessarily correlated with anything.
What about porosity?
There's no porosities in these samples that I'm aware of. Okay, so, but porosity is a completely important problem for additive manufacturing as well. This is another issue that affects fatigue life in additively manufactured samples. It all depends on the material system that you're looking at. So with 316L, they have been able to create samples with a very low porosity as far as I understand from these techniques. If you look at titanium, typically if you try to make titanium alloys, you get a lot of cracks, you get a lot of porosities, and so on and so forth. So it all depends on the material. So, okay, so now I've hopefully, and I can tell you, so this was actually a complete part that was developed. I believe it, you actually do multi-layers of depositing materials. Again, this is just a close-up, and again, you cannot really see it from this projector, but nevertheless, it's the same idea. But then our collaborators at the Navy, they actually did single pass of a laser. So they put a powder, walk just with one laser pass on the sample, melt it, and it solidifies. And this is basically what you're seeing. That's the melt pool that solidified. and it actually extends down a little bit down here. And then again, they did a lot of different studies of trying to characterize what is happening. And again, they see these very similar cellular structures that align quite nicely with these chemical segregation. So it happens regardless of the number of passes. But what seemingly people have been reporting is the more deposition that you do, the more thermal cyclic type of behavior the material is going to experience, the more clearer these cell walls are going to form. These high dislocation density regions forming cells are going to be much more clear. You can see here, they're much more well defined as compared to this experiment with a single pass. So actually our collaborators from the Navy came to us and said, okay, we understand that these are unique structures. We don't understand why did they form. A couple of things that I actually missed to say, and it's not entirely clear here with the color again, but these dislocation walls, these cells typically have walls that are aligned along particular directions, which are 100 directions. Why that was a puzzling question, that's where these, again, the molybdenum and the chrome walls are. They're, again, aligned along these same 100 directions. If you do fatigue experiments, as an example, or if you do mechanical loading on a sample, typically you get cells forming, but the cells typically won't be aligned along 100 directions, but they would be aligned along the intersection of slip planes, and thus you're going to get more of 110 type of alignments. So first of all, the puzzling question that they had is where these cells, how do these cells form? Where do they form? But in addition, again, how do you actually use that, or why does that end up influencing the mechanical properties significantly? So this is just an example of, this is cyclic loading of, in this case, it's another FCC metal. I think this is copper, nickel, but the behavior is very similar even for 316L. If you do cyclic loading, depending on orientation, depending on the magnitude of the plastic strain that you're cyclically loading about, you get these very nice dislocation structures that are forming, right? And if you compare this type of behavior to the previous image, they're very, very similar. So it indicates that there's something that is happening as these materials are being cooled down during that cool down process after the melting and after the solidification that lead to these types of structures. So again, we're trying to understand it from that kind of sense in a little bit more details. So the challenges that we've been facing as a center, we were interested in trying to predict how does the segregation happen. I don't do segregation, I don't do phase field, so I'm not going to look at that at all. So for me, we just assumed that the chemical segregation is a result, but our collaborators, we had collaborators from Northwestern that were actually interested in trying to model that behavior. For us, we're going to start off with that, okay, we know that from these phase field simulations, from these types of calculations, is that you get chemical segregation. It's very similar to what happens during welding. During welding, you can get segregation of heavy elements as the solid front basically propagates into the melt pool. The two questions that we could address is, one of them is related to, can we predict the evolution of these dislocation microstructures during the cooling down stage after you've did the one pass or multiple passes of this laser? And can we actually predict how these types of microstructure influence the mechanical properties? For the interest of time, what I'm going to be focusing on predominantly here is this green region, which is, can we actually predict this evolving dislocation structure? And then how can we use that to ultimately feed into into simulations that actually want to do predictions of the mechanical properties of parts that were made out of this LPBF type of processing. Okay. So how do we do that? Again, it's a multi-scale type of problem. As I showed you, there's dislocation structures that are forming. And what we're going to try to do is look at that specific scale. The reason that we look at that specific scale, because we can actually look at evolutions of dislocation structures at the microns scale, microns, tens of micron scale. Atomistics is great. It actually has less assumptions than what we do in discrete dislocation dynamics. I'll talk to you in a minute about what we do in those kind of simulations. However, they're still limited. Regardless of how many processors you have, you won't be able to go above a few microns. And the problem is these structures that are forming with some type of structure that are larger than that. And your grains are typically larger than that. So it's very important to be able to understand on a grain level what kind of structures are evolving. So we're going to try to do these predictions at that coarse grain level, but to be able to do that, we need information from atomistic scales, and I'll tell you what these kind of information we need. But finally, the end goal is when you get this information, that doesn't tell you anything about the part over there. It can tell you local properties, but ultimately you need some type of tool, intermediate tool, that allows you to be able to go to multiple grains. You look at sample size, and that is beyond the capabilities of these coarse grain approaches. So we need to be able to input information into crystal plasticity models such that we can get into the coarse grain level. So this is precisely what I'm going to be talking about today, is that the simulations, the bulk of the simulations that I'm going to present to you is this length scale, getting information from lower length scales and trying to extrapolate information into upper length scales such that these crystal level type of simulations can actually be physics-based informed as compared to just doing an experiment and then curve fitting data and then trying to come up with constitutive laws that represent that type of behavior. A lot of the new stuff that we're trying to push forward with, and I'm not going to have enough time to go into, is that we're actually trying to do this upscaling with machine learning. There's tons of data that is generated from these types of simulations, and we can actually utilize machine learning to learn from it patterns that allows us to better predict and develop constitutive laws at the crystal level that are much more important. And then you have to use experiments, so this is the modeling side, but you have to do experiments at the same appropriate length scale that you can couple with it. Again, for today, I'm not gonna go into that, and given that this is a workshop that is focused predominantly on the models, but the one thing is, I'll show you throughout that we are actually trying to couple with experiments and show that we're actually doing predictions properly. Yes?
From the crystal level to crashing a car, that's still quite a bit.
Yes. So there's homogenization approaches that involve taking crystal plasticity level simulations and then try to do large-scale FEM simulations. But now,
empirical plasticity.
not empirical based. So there's a lot of more new techniques. There's the classical empirical approach, but the classical empirical approach does not take into consideration the microstructural influences. So there's a lot of people that work on this level that try to develop homogenization techniques as well as some type of approximations where they can extract information from the crystal level if they have tens of grains, because again, they have an issue with numbers because the larger the simulation volume they have, the number of equations that they're trying to solve become huge. They're not able to get to a component level structure, but you can inform the FEM simulations a lot with these types of crystal plasticity analysis. Okay, so what are we doing? So what we do in my group is really the pink region here. So what we want to do is understand the crystalline dislocation, the crystal dislocations and how they evolve. So we want to model the cellular dislocation networks and how they're evolving during the cool down. But to be able to do that, we need a bunch of information. That information comes from experiments, comes from DFT, comes from FEM calculations, and comes from MD simulations. What is that information? Well, for one, we need actually the information related to the loads that are generated and the temperatures that are generated when a laser passes through and this material starts cooling down. Because the cooling down of the material induces significant amount of residual stresses that will affect the evolution of the dislocation microstructure during that cool down stage. So we need that information, and I'll talk about that in a minute. But the dislocation dynamics, traditionally the discrete dislocation dynamics have been typically focused on pure metals. We typically used to like to look at nickel, copper, these nice metals that no one actually uses as pure metals. So we need to really be able to account for that we are actually now looking at alloys. So to do that, we need information from atomistics that relates to cross-slip activation energies, relate to dislocation mobilities for that particular alloy that we're actually interested in. We take that information, generate it. This is the work from our collaborators at Georgia Tech. That information feeds into our simulations as well on the discrete dislocation level. We need information from the experiments about how they're actually fabricating this. We need the energies associated with the lasers and so on and so forth, so we get that from our experimental collaborators. But in addition, there's a lot of information that is needed from the DFT calculations related to the diffusion of the elements, related to the interfacial energies and so on and so forth, to calculate these defect formation volumes and the vacancy formation energies and so on and so forth. Ultimately, what we're trying to do, as I said, be able to predict microstructure evolution, be able to use that to identify the long-range internal stresses that are developing in the heterogeneous dislocation structures, such that these crystal plasticity simulations that are higher length scale than us can actually be physics informed and account actually for these particular microstructures that are evolving. Okay, so how to model the effect of heterogeneity in solid in solute. I think this is probably a typo, and I'm getting a little bit tired, but nevertheless, we're trying to basically look at the effect of the heterogeneity in the chemical concentration and how does it affect the dislocation microstructure. So what we're gonna do is discrete dislocation dynamics. What is discrete dislocation dynamics? This is my one slide to explain it for anyone that hasn't seen it before. Everyone here probably knows atomistic simulations. You know atoms, you can do atoms, you can look at how they evolve. Every atom is in the system, you can have a defect, you can look at the dislocations and so on and so forth. That, in an experimental analogy, is nothing but high-resolution TEM. So what is discrete dislocation dynamics? Well, in reality, there's a lot of atoms here that don't do much, right? The defect is really this guy here. This is the defect that eventually evolves. So what discrete dislocation dynamics tries to do is look at particularly that defect alone represented in a coarse-grained fashion as lines that are evolving in space, because dislocation are nothing but dislocation loops. So this is a coarse-grained representation of the atomistic simulation. This is actually a DXA out of, this is a software called DXA, which extracts the fronts of the dislocations as lines and identifies their shape and identifies their Burgers vector and so on and so forth. So this is not a discrete dislocation dynamics representation, but represents what we do in a discrete dislocation dynamics.
Is it a written image?
Yes. So this is DXA, which is part of Ovito, to extract basically the dislocation front. So you have two partials here, you can extract that, and you can identify what the stacking fault is, and so on and so forth. So it gives you a representation of coarse graining, right? You removed all the atoms that don't matter to me, and you only represented the defects themselves that I'm actually interested in. Okay? That is nothing but traditional TEM. So what we're trying to do in the discrete dislocation dynamics world is looking at the evolution of dislocations at the level of traditional TEM. The major difference is TEM requires very thin foils to be able to observe these dislocations. In the discrete dislocation dynamics world, I can actually go to microns, and tens of microns actually, that the TEM experiments are not able to access. So that's my one slide introduction of what discrete dislocation dynamics is. In my group, over the years, we've been trying to, so what is dislocation dynamics now? So if you assume that this is one of those lines that I showed you previously in this previous plot here, if you take one of these loops that are forming, you can break it up similar to what you do in an FEM. Now these are linear segments. You can write equations of motion. These are actually quasi-static type of equations of motion. You can calculate forces on these dislocations, and you can solve these quasi-static equations and evolve the dislocations over time, and thus you can actually get a better understanding of how these dislocations are evolving. And you can do, traditionally we've done these types of relatively large simulations of 20 by 20 by 50 microns, so this is relatively a huge volume, and you can look at evolution of dislocation microstructure. This is simply under compressive loading or tensile loading, and look at the influence of the orientation of your loading or your crystal on the dislocation structure formation. You can predict what the hardening rates are. So it gives you very nice information of not just the dislocation microstructure, but the stress strain curve. And you can identify local dislocation densities and so on and so forth. You could do a lot of more intriguing things of looking at surface roughness. If you have a surface as the dislocations exit, you can actually predict the steps that are forming on the surface. If you have boundaries and interfaces, you can actually model that. So this is a case where we had twinning in magnesium, and you can look at dislocation twin interactions, and only showing you the twin boundaries and how they're evolving due to the dislocation interactions with those boundaries. You can look at multi-phase alloys as well. So there's a lot of unique tools here and a unique set of analysis that you can utilize and you can build into these models. Again, a lot of this type of information is really upscaled from MD, but upscaled in terms of physics. I want to identify what are the physics that relate to the motion of these dislocations and how they react, and we build it into our model. So even though that we can do these simulations and you would have 1,000,000 degrees of freedom, or million nodes, so multiply by 3 to get the number of degrees of freedom, so 3 million degrees of freedom, they're much less than the trillion number of degrees of freedom that you get from atomistics. But these simulations are much more computationally expensive because of all the rules that are embedded. MD simulations, basically all the rules are atom interactions, right? Here we actually have to have rules related to how the dislocation reactions form and so on and so forth that are, again, based on the MD simulations, But when you upscale that information, you're still limited to millions at most with these types of simulations, millions of nodes or millions of degrees of freedom as compared to trillions. I don't know if we're ever gonna reach trillions with the current techniques or not, but that's where we are right now. Okay, so how do we model then the behavior of the cellular solidification? So as I said, I don't care how these cellular solidifications form, how these chemical structures form. I'm gonna just take them from experiments. So if you approximate it, it's basically the black lines here represents the molybdenum and chrome rich regions. We know the sizes of these cells, we know the sizes of the walls, all that comes from the experimental characterization. So we build that in a schematic representation. So the representation that I'm showing you schematically represents where these high chrome and high molybdenum regions are gonna be. And they basically form this specific structure of a grid. If you're looking down along the 100 direction, then it's gonna be like a grid. If you're looking on either one of these side views of 010 or 001 direction, they become more of an elongated type of representation. And I'll show you, again, some of these other experiments that actually show that a little bit more carefully. But experimentally as well, we know the local composition. I know the local composition in the cells and in the high molybdenum and chrome rich regions. So I have that information experimentally. But now here comes the problem. As I said previously, a lot of the simulations that we used to do in the past are on pure metals. But now we're not talking about a pure metal, we're talking about a heterogeneous alloy. And in addition, there's solutes all over the place that influence the behavior of the dislocation. So how do we account for that behavior? That's a very important aspect. So the idea that we started off with here is actually using the solute misfit induced resistance to dislocation glide as a measure that we can put into our dislocation, discrete dislocation dynamics. The solute misfit induced resistance to the dislocation glide is gonna be different in the cell as compared to the walls. Why? Because the composition is different. So we can actually do that. How do we calculate that type of influence on the residual, on the gliding of a dislocation? It happened that Bill Curtin's group over the last, I think 10 years, I forgot when that paper was published. Unfortunately, I don't have the citation here, I have it on the next slide. But nevertheless, they came up with a statistical model that represents the motion of an individual dislocation through a solute field. And from that, they were able to calculate what, or represent the influence of the solutes on the dislocations. So we take that, and again, it's based on the solute misfit induced resistance stress. So we take that as our model that I'll show you in a minute. But in addition, the dislocation is still moving with a certain velocity stress relationship, or it has a velocity stress relationship that we have to identify for the specific alloy. So that's another input that we're gonna have to develop. So this is Bill Curtin's model. So it was developed I think it was actually in 2014, 2012, stand corrected. But nevertheless, it basically calculates the resistive stress or the critical resolved shear stress of a single dislocation that is passing through a field that has a certain concentration, and you can calculate it as a function of temperature and your strain rate of your loading. And to calculate that value, then you need to calculate this energy component. That energy component relates to the local concentration, relates to the change in volume associated with the different atoms, and so on and so forth. So nevertheless, this is the bunch of equations that you can use. Plug in your concentration, get data for the misfit volumes from your DFT calculations or some type of approximation, put it into your model, predict what a critical resolved shear stress is at any point within your simulation volume. If you look at the cases of the concentration in the wall or the concentration in the cell interior, and you do this prediction of that critical resolved shear stress as a function of temperature, these are the two curves that you would predict. So the red represents the cell interior, the blue represents the cell walls themselves. Now if you look at the traditional yield strength of 316L, not the 3D printed alloys, but the traditional ones, this is where it's gonna fit. Now it's clearly higher than both. Why? You have to realize again that this model that was based on actually statistical analysis and as well validated with MD simulations have only focused on a single dislocation. So while they actually call this the yield strength, it's not a yield strength, it's a critical resolved shear strength. The yield strength depends on the types of dislocations and the evolution of those dislocation networks. and the dislocation density and how it evolves. And thus, that's typically why the yield strength is always going to be higher than any prediction that you're going to get. So nevertheless, just to show you the difference in the behavior, even though that this is not printed and we don't have the full temperature space of the 316 printed samples, so just showed you here for comparison just to make that emphasis that this is actually a critical resolved shear stress, not a yield stress. So it relates directly to what we do because we need the critical resolved shear stress to activate dislocations. Now, as I said, as a dislocation moves through that field, it will have a certain velocity, and that certain velocity, you can write an equation for the velocity versus the force applied on the dislocation, and you're going to have a drag coefficient that you can calculate. So this is our collaborators from Georgia Tech. They looked into different types of potentials that exist out there. Unfortunately, there's no one EAM potential out there that represents all the elements of 316L, but there was one that has at least chrome, nickel, and iron. That was the more complex, more sophisticated EAM that they could find that actually gave them meaningful results from the MD simulations. So they did this for different concentrations of nickel and chrome, and we used that as an assumption given the concentration of nickel and chrome that we are aware of in the 316L samples that we're doing, given the concentrations in the cell walls and the cell interiors, and we use those results from here and incorporate that into our MD simulations. So this is an assumption. This is the weakest link, in my opinion, in the model so far, because it's assuming a different, or it's using a drag coefficient of an actually slightly different alloy. So what is the influence of molybdenum? It can have actually a little bit different of an influence, but I'll try to show you that it actually doesn't have a significant influence for the questions that we're trying to answer. Okay, so those basically are our inputs from the atomistic simulations. But then now I need the stress profile and I need the temperature profile to understand how the dislocations evolve. So how do we do that? We did that with physics-based, or multi-physics, I should say, finite element simulation. So this is actually done with FEM type of calculations, but multi-physics FEM. Without going into too much details of it, I don't like FEM too much. To me, it's straightforward. But nevertheless, you need elastic modulus versus temperature. So we actually dug through literature and identified for 316L what is the elastic modulus as a function of temperature. You do need a yield strength as a function of temperature. So this is, again, data that was extracted from literature. You can see the citations associated with it in our paper that was published last year. Nevertheless, this is your input. You set up a simulation. This is, again, it's a symmetric type of behavior. The laser is going to come down here and pass through that process. You know the actual speed of the laser, so you know the amount of energy that is producing into the sample. So you can model all of that. You know the laser size and so on and so forth, or the spot size. So you can model all of that and input that into the model. So we'll assume that we know how that model is generated. You generate that, run the simulations. These are the types of predictions that you get. What you're seeing here is the 3D temperature profile. Down here, I'm showing you the evolution of the 3D von Mises profile. Now, if you take any cross-section, this would be a cross-section representation here, and I'm showing you here the evolution of the von Mises stresses again on that cross-section. And you can see clearly that the different von Mises stresses or different locations in the cross-section have different types of stresses because they're actually experiencing different type of temperatures. And one additional thing to say, we're actually doing the melting and then the solidification here. So when the material goes, above the melting temperature, actually is the elements over there are not contributing to the strengths. But as soon as the solidification happens, those elements come back in and you can calculate, again, the idea of residual stresses as they form. Now, these are on the scale of millimeters. We don't do millimeters in discrete dislocation dynamics, but we can do microns. So the way that we attempted to do this is we said, okay, if I know the stress distribution at different points, I can actually represent dislocation structure evolution at the different points. So for what I'm going to show you in the rest of this talk, we chose this point here. If you choose that point and look at the temperature profile, that's the red curve. If you look at the stress components or the components of the stress tensor, all the 6 components of the stress tensor, this is how they basically evolve, or this is how our model predicts they're going to evolve for that particular point. So now I actually have a temperature profile and I have an associated stress profile. It's a multi-axial loading stress state that you can put into your discrete dislocation dynamics, knowing, again, the cool down and the temperature that you're at. You know what the stresses are, and thus you can do an actual simulation with discrete dislocation dynamics. Now, as I was saying, it is a complex stress state. So if you actually look, given those stresses and how they're evolving at that one particular point. You can actually calculate the Schmidt factor on the different planes. Yes?
I'm just wondering, with that previous slide, is there any way that you could do things almost kind of self-consistent?
Yes. We are not doing this self-consistently right now, but we ought to do it in the future if you really want to do the coupling, but you're absolutely right. Okay.
But presumably that would make it a lot harder.
Yes. It's a lot more time consuming to do the coupling problem. So when we started these simulations 3 years ago, we decided just to do them decoupled. This is, again, approximation, which we think is a reasonable approximation for what we're trying to develop in these kind of analysis. Okay, so the complexity happens in terms of the Schmidt factor per slip system as a function of temperature. As the temperature decreases, you can see that there's fluctuations and changes in the Schmidt factors on the different planes. So those that were active early on at high temperatures might be inactive later on, and then might kick off again and be active. Similarly, some that were very active at the beginning, they're continuously declining. Some that were inactive at higher temperatures, eventually as the temperature increases, become active. So this clearly will indicate that there has to be some very complex dislocation structure that is evolving to accommodate these types of variations in the Schmidt factor as a function of temperature. So let's transition into the results. All of that was introduction and methods. How much time do I have? Okay, we'll get there. I speak fast. That's why I'm sweating. So the results. So the first result that we actually generated was the following. We said, for me, or I basically said that to the postdoc as he was doing it, when we were trying to attempt to do these simulations. These are 10 by 10 by 10 micron simulation volumes. We want to do the cool down. I want to start off from the point where the material solidified. So this is right after you the melting temperature, your temperature decreased below the melting temperature point. And then now you have a solid material, and I want to cool down the simulations. And I want to do the simulations of the cool down. But I thought at the beginning that this is going to be impossible. So I said, okay, let's make an approximation here and start off with, I'm going to just model the behavior of the dislocation at 700 Kelvin. At 700 Kelvin, I know what the stress state is. Let's build that into our simulations and let's see what happens in the dislocations. And we started off with an initial dislocation density of 10 to the 12 as an assumption. Fine. Maybe it's absolutely wrong, but let's just keep it for now and I'll show you better results in a minute. I don't know why this is stuck. Okay, movie's playing now. We had a bunch of lines and now we have spaghetti balls, right? That's all it is. It's a bunch of spaghetti. But if you look closely as this movie repeats, and if it does repeat, maybe I shouldn't try to make it repeat. Actually, here we go. You might start seeing alignment. The orientation that I'm choosing here, actually this orientation is 100 and 010. You might faintly see, if the projector was better, that there are actual dislocation density, high density walls that are forming. And these are actually forming along these specific lines, okay? So I'm assuming that you guys are going to believe me, but if you don't, we can actually go in and actually quantify that. So how do we quantify that? So a couple of things that I'm showing you here. This is not actually an evolution of dislocation microstructure, but to tell you the idea of that we're representing things and similar to what TEM does, this is actually snapshots, not snapshots, but these are actually foils that we're cutting through the sample, and we're showing you the actual dislocation structure in each foil. I think these were 1 micron foils through the 10 micron sample to 10 micron thickness, and we're showing you what the dislocation structure would look like in each one of those foils, and we're just repeating them to show you all of them. But if you actually do the calculations of the local dislocation density, so this is what we're representing here, for the entire sample and collapse it onto a 2D plane just to see it in 2D, this is what you get. The red represents high dislocation densities, blue represents low dislocation densities. Right away, you can clearly see the quite nice checkered pattern, right? The neat thing, again, with the dislocation dynamics and that you have all the information with the dislocations is that you can actually do two-point correlations into your calculations. You can look into the dislocation structure, generate 2-point correlations, and identify if there are any specific patterns that develop. And again, if you do that in this specific orientation that we're showing you here, which is an 010 versus a 100, again, you can clearly see that there is a pattern that is forming. The yellow represents that pattern. That there's a very nice pattern that is forming along these high dislocation density regions. If you look at it from this point of view, so for doing an orientation this way, and you do the 2-point correlation, you get these types of patterns. So They're elongated. There's nothing horizontal. It's all elongated. How does this compare to experiments? These are the actual experiments. This is that 100 orientation that I keep on showing you here with that checkered type of representation. This was a TEM foil that was extracted in the other direction. So now you see these elongated channels that are forming. And again, if you look at that same behavior, in that case, you'll see the elongated channels that are forming. So it gives us a better feeling that, okay, we're actually capturing this type of behavior. This analysis is allowing us to show that actually the chemical segregation or the higher concentrations of molybdenum and chrome are actually resulting in the dislocations being pinned along these chemical walls and thus basically being trapped, and thus that's where you're getting these high dislocation densities. We can repeat these experiments at different temperatures. Yes?
If you go back to that movie,
Which one?
this is very fast, right?
Yes.
Right? Everything seems to be everywhere.
Yeah, so this is again, this is not evolving over time, but this is the last time step, and I'm showing you slices on top of one another.
So eventually the more static picture that you'd have, because dislocations should somehow aggregate into subgrain boundaries or something by elastic interaction, still holds.
Yes.
It's just different.
Yes.
So the TEM image is actually, because the TEM images always look beautifully and static.
So this is the static image of a TEM. This is actually a TEM. This is one of the cases that I showed you out of the 10 slices. This is just one slice in the orientation that mimics this TEM image. This is that one slice in the other direction that mimics this direction.
So what is the linear size of your sample?
What is the?
Linear size.
The size of the entire simulation cell is 10 by 10 by 10 microns. The foils are 10 by 10 by 1 that are extracted out of the larger simulation volume. And I'll tell you right now, because I don't know if I'm going to get time to.
Would it sacrifice something?
Say that again?
You reduce your length scale to 1 micron. Would it sacrifice something?
So if my simulation is 1 micron, is the volume is 1 micron, what I'm going to tell you is the 10 by 10 by 10 is actually wrong. So it was interesting because we knew this later on, that the simulation cell size actually really matters. It is not wrong in this assumption because I started off with a high dislocation density initially. I went through it quickly and I said, we're going to do a simulation at 700, but I'm going to assume it to be 10 to the 12 dislocation density. I don't know what it is because experimentalists don't know at that temperature what the dislocation density is. But let me get to that point because it's a very important point, and I think it relates to what the punchline that I want to get to. Yes?
Can I just check the grid pattern? That's effectively an input. You put in the concentration.
The position of where these grids are forming are where I'm putting the high concentrations. Yes. So what we're concluding from this is clearly the presence of these solutes are leading to these patterns. But we can do the analysis as a function of temperature. And again, we didn't do the full cool down in this set of simulations, but I just decided to run a simulation with the chemical walls, but at 1300 and let the simulation run for a while. Do it at 1100, do it at 900, do it at 700, and so on and so forth. And you can see that the patterns don't form at these high temperatures with the set of simulations that we did over here, but they start forming when you go below 1000 degrees. Why? Because now the solutes have a higher influence on the pinning of dislocations at these higher temperatures, at these lower temperatures as compared to high temperatures where the mobility is quite fast. Other questions? Okay. Let me, in the interest of time, skip this. There's a lot of analysis that we could do. So one other example is if you change the laser power, what happens is that the cell structures are different. You still get the 100 oriented cells, but on a larger scale. But interestingly, internally, you start getting alignments of dislocations along a 110 orientation, which is the typical when you have general plasticity. We did these types of calculations, again, the simulations at 700, and if you do that, you can see that again, for the case of the smaller cells with the higher energy, you see the patterns that are forming. For the case of the lower energy, the larger cells, you still see those same alignments happening. But interestingly, internally, you start seeing these patterns that are forming along 45 degrees, which is basically that argument of that these dislocations are forming not due to solid solution, not due to the solute dislocation interactions, but due to the dislocation interactions themselves. So it allows us to give us a better physical understanding of the origin of this. So when we did this, it was fine, and we published it, and we were like, okay, great, we did very good work. But I wasn't satisfied. Why? Because I didn't do cool down. I actually want to see the evolution as the cool down happens. So we actually did this very recently. This is a paper that is still under review. But you can look at the evolution as a function of temperature. So I'm actually decreasing temperature in my simulations, and my stresses are changing as a function of time with a particular cool down rate that I'll mention in a minute. But nevertheless, this is how the dislocation structure is going to evolve. Again, if you look at it this way, it's a bunch of spaghetti. But if you look at it in terms of the correlations, you can start seeing that initially at 1200, very little correlations. 1500, maybe there's some correlation about 45 degrees. But suddenly, as the temperature continues to decrease, voila. That's my attempt to do French. You get the you get the pattern starting to form at these lower temperatures. So initially at these higher temperatures, you're getting junctions from dislocation reactions, but as the temperature continuously decreases, the solutes become more and more important and influence the behavior, and you're getting these types of patterns forming. Let me skip this just as, again, to tell you that we can actually look at the dislocation density per slip system, correlate that with the evolution of the Schmidt factors and so on and so forth. One point, just so no one understands that I actually did the cool down all the way down to room temperature. I didn't do anything, the postdoc did it. He did not do it all the way down to room temperature, but we had to stop at 1100. Why? Because the dislocation density is astronomical for us here. It's about 10 to the 14. 10 to the 14 for us is about 1 million, it's about 3 million data points. We've been running that on 1,000 processors, 1,000 cores, for about a month. It's a huge simulation, but it was important for us to be able to see how that dislocation microstructure is actually evolving as a function of temperature. So this is trying to push it beyond that. We need more computational access, but hopefully maybe in national labs they can do these types of simulations better. You can actually do a lot of intriguing things now with these types of simulations because you can vary the cooling rate. There is a given cooling rate that you get from the experiment, but you can say, okay, maybe I'm going to lower it, maybe I'm going to increase it. So the intermediate is the one that we have similar to the experiment. Higher means that we doubled the cooling rate. Lower means that we divided by 1/2. You can see the evolution of the dislocation density, total dislocation density. They're different. The dislocation actually starts multiplying a lot more faster for the lower cooling rate. Why? Because you're giving the dislocation more time to activate at that temperature. But nevertheless, if you look at the actual density of the dislocations in the walls versus the interior, the cooling rate doesn't really have an influence. So if you're only interested in understanding the mechanism of how these walls form, maybe this doesn't really matter. Maybe the cooling rate doesn't really matter. The other intriguing thing here is, if you look actually at room temperature when they do these TEM foils, they extract the dislocation density. That dislocation density is up here. So it's on the order of 10 to the 15, 10 to the 14 plus. We basically reached 10 to the 14, but you can see that all of them are trying to transition, and eventually if I'm able to cool this down further, we think that ultimately we should reach that dislocation density, but we're lower. And if you compare the TEM images versus our dislocation dynamics TEM images, you'll notice that our densities are actually lower than those in the experiments. And we know why. It's just I haven't cooled it down all the way down to room temperature yet. There's a lot of intriguing physics that they have observed in an individual grain experimentally. This is one single grain. They've actually identified 2 different sets of traces, and they went in and identified that the chemical structure only is present in this lower half part of the grain. So you can build that into the simulations, and that's what we did. So again, the grid is in the lower half here, represents what they're seeing in the experiment. The chemical structure is only forming in 1/2 of the grain, where the other half is more homogeneous. You can run your dislocation dynamics. You get a spaghetti, do your analysis, look at different regions. In the lower half where you have these cells, you can potentially see the alignment. In the upper half, you don't necessarily see a very well alignment. Maybe it's aligned along at 45 degrees. If you do the 2-point correlations, you'll see them again. For the upper half alone, you have more or less a random distribution. I won't say it's actually aligned along a particular direction, but for the lower half, you can clearly see the cell structure forming along these chemical cell walls that are forming. So again, we're not trying to answer or address the question of how these cells form, but we're trying to understand how do they influence the dislocation microstructure. And we're showing again that we can actually capture that quite nicely with these kind of simulations. Okay, so here's the challenge. All of this is quite nice. I think it's quite nice. Good predictions and all. But the bigger question of why we actually started down this route was to be able to upscale that information, upscale that heterogeneity in the dislocation evolution, and the heterogeneity in the internal stress states into crystal plasticity. So how do we actually do that? So the way that we thought about it is that you definitely need to learn what is happening in these simulations. We definitely need to learn from machine learning or have machine learning learn it because it's just significant amount of data that is present. The one point, my joke here, it's not my joke, someone else's joke, but I copied it from the internet, is about that machine learning works quite nicely, right? But you have to be very careful because if you train machines on historical data that actually exists, you actually might fail. They might fail. Why? So if you look through history, what happened was most wars that were won were with primitive weapons. So if you train machines on the history, they're going to fail, right? So the punchline here is that we need to be able to design simulations. We need to design calculations that must be really clean and carefully designed such that we don't fall into the trap of we're just training some crap and it gives us some crap, right? So how do we do that? So we were quite lucky because when we started these when we started this project, actually the reason that we started this project was that our high performance computer was in a transition period. We had another 20,000 type of cores that were being installed, and they needed someone to run a test case. So we were like, okay, let's design these simulations and let's go crazy with them. So what's the crazy idea here is that we're actually trying to push the boundaries of discrete dislocation dynamics to go to large, significantly large volumes. This is humongous for a discrete dislocation dynamic type of calculation. And why did we want to do that? Is because something that I missed to, or I did not want to mention early on, is that there is a clear influence of the initial dislocation density that you're going to choose in the simulation. I don't know what it is experimentally, but I have to make an assumption. My educated assumption is it must be very low at the right after it solidifies. That's an assumption. It's a very high temperature. You just solidified. There is going to be dislocations, but I don't think that there are going to be high dislocation densities initially. So if you assume that the initial dislocation density is equal to that dislocation density of an annealed material, 10 to the 9, and you design a simulation cell that is a 20 micron versus a cell that is a 50 micron versus a cell that is 75 micron, randomly generating loops, so each one of those is a random loop that was generated, assume that they had generated during the fabrication process. And then you look into each one of those sizes, and what I'm showing you here is the comparison between the 75 and the 20, so the larger and the smaller. And if you look at the distribution of the dislocation densities per slip system, there should be a shaded region here for the green that you don't see, but the shaded region for the green actually spans this entire region here. So it would tell you that some slip systems would not have any dislocations at all if you assume that the simulation volume is 20 micron. Because it's a random process. I'm generating the dislocations randomly, so you might miss some because the low dislocation density is low and your sample size is small. Only when you go to these large samples, then the dislocations per slip system when generated randomly are very consistent. So this is the range of dislocation densities per slip system at different initial dislocation densities for the 75 and the 20. The shaded is the 20 and the solid is basically your 75. So there's clearly an influence here. So then the question was, okay, so if we actually design simulations 75, 50, and 20, and let's actually do the full cool down now more properly for these three cases and let's see what we get. This is what you start getting in these three cases. And I'm showing you the actual simulation results at the end of the simulation time, starting with a very low dislocation density of 10 to the 19, down to, I did not report the temperature here. Oh, I actually do report. And this is only down to 1400 Kelvin. So we haven't done the full cool down, again, because these become very crazy kind of simulations to run. But you can start seeing, okay, here you can clearly see a very well-defined set of walls that are forming. Here it's a little bit more complicated to see, but you can clearly potentially see the different orientations. The 75, again, a lot more complex. You could do TEM analysis. Actually, before you do the TEM analysis, I'm just showing you here the periodic cell. So the box here is the 20 micron cell, and I'm showing the periodicity in a 75 micron cell. Same thing for the 50. This is the 50 cell, showing its periodicity, and then this is the 75, just so you can actually have a one-to-one representation. You can clearly see that this location structure is completely different. They're way well defined down here, and much more complex up here. Why is that? We'll get to that in a minute. Again, you can do TEM foils. This is a TEM foil extracted from the 20 with periodic cell in 75, 50 and a 75 and a 75 TM foil. Again, you can see very distinct differences in the dislocation structure, very more complex, very more random, a lot more representative of what they see experimentally as these very well-defined patterns that are forming. You could do a lot of analysis and understand the evolution of dislocation density and the junctions per slip system. So this is for the 3 different cases. And right away, you'll see the evolution of the dislocation density per slip system here. If you run this for different cases, they're different than the 50 or the 75. The 50 and the 75 are close to one another. They're not identical, but they're actually activating the same subsystems, and the evolution rates are reasonably similar. You can clearly see the revolution rate of the pink case here is actually a little bit higher. Just 2 more minutes. So, okay, so that's great. So that basically starts off to give us big red flashing light, that's what I'm trying to find, that even when you did these huge simulations, this is huge for the discrete dislocation dynamic community. Regular community that do discrete dislocation dynamics, 20 micron is huge. So even with that huge simulation, if you start off with what you think is actually physical initial dislocation densities, we're clearly not going to build the dislocation structure the way that we think that they should happen. And thus we really have to be able to do a more representative volume element, which we think is actually closer to this range of length scale for these kind of calculations. So there's a significant influence of this RVE. Okay, so how do we actually learn from any of this? So what we are starting to do is take this 75 micron simulation, and now if I want to actually upscale information to crystal plasticity, they don't care about the actual dislocations per se, they care more about evolution equations. So we can actually identify regions in the different crystal. We can create different subvolumes into the large 75 micron volume and look at the actual flow, the actual flux of the dislocation through the boundaries of these subvolumes within your large simulation as it evolves. And you can look at how those subfluxes, dislocation fluxes, are evolving over time at different locations in the crystal, which gives you a lot more meaningful information as compared to just doing one simulation and trying to extract one density as it evolves in time. But you can actually get now location-specific analysis. In the interest of time, we're trying to do these kind of analysis and trying to push forward with it. But in addition to that, it's important not just to understand a scalar quantity of a dislocation density, but you really need to be able to understand the structure and how is it evolving. So I have a student currently that is doing graph networks and trying to represent these dislocation networks that we have as graph networks to better understand how these dislocations are reacting and evolving in these humongous simulation cells. I know that I went a little bit over time, so I'll keep my conclusions up here, and I'm happy to answer any questions.